Hi, Artem here. Recently, a YouTube channel by the name of Deckard made a video concerning a specific type of cellular automata, such that each cell has two parent cells instead of the normal three. And by the way, you should probably watch that video, as a lot of what I say in this video will not make much sense if you haven't seen that one. But I think I have found a new way of thinking about such automata, and it shows that the boundary between order and chaos is much more blurred than we previously thought. So, a quick recap. In a Pascal-style cellular automata, we start with the infinite diagonal of a certain color, and then we go row by row applying the rules of the cellular automata. With two parent cells and three colors, and it being transitive, there are six possible combinations of parent cells that could yield different results. Each unique combination of such results yields a different rule, making for 729 different rule sets, although it's less if you account for symmetry. Now, to find a more scientific way of categorizing rule sets, Descartes invented his own naming system that tries to categorize patterns but gets progressively more wacky when the patterns get more complicated. But his most simple unit of measurement is a shell, an infinite diagonal line of cells that has a certain pattern to them. But then I had a thought, because I realized that's actually all you need. Let me explain. Look at this cell and now ask yourself the question, which cells could hypothetically have impacted this cell's state? The answer is these cells. Every cell that is above the diagonal line to the right. The reason for that is in such cellular automata, the cells cannot propagate faster than one cell to the left or right per row, and we call this effect the speed of light of the cellular automata. In fact, this is what creates the first shell to begin with, as it is just a cell propagating at the speed of light. With that in mind, let us look at this whole shell of cells and see that the only cells that can impact cells in this shell are the cells in previous shells, in this case just the one, and the cells in the same shell. Now, as the pattern is symmetric due to the transitivity of the rule set, if we start a shell from column 0, then the first cell would be impacted by this cell and its mirror counterpart, and then only by corresponding cells in the first shell. And as the first shell is clearly periodic, it follows that this shell must be periodic as well. And it follows for every other shell after that. But there is an exception, because remember, the first cell in a shell doesn't interact with the cell from its own shell, but rather only by cells from different shells. Now, what we will find is that this can cause the first few cells of a shell to be different before falling into a stable pattern. In fact, Descartes knew this and in simple patterns called them cells, and I like to call them transient cells because they transition into a stable pattern. Now, with this in mind, each cellular automata pattern can be described with the sequence of each shell in order, and that it is the simplest and most fundamental form of the cellular automata. And while we can perhaps find it easier to just look at the patterns visually, what I realized is that its most fundamental level, a cellular automata, is just a sequence of shells. And also this means that each cellular automata rule set can be easier understood and categorized mathematically. Now, let's look at some of the simpler repetitive patterns to get a feel for how these shell forms work. For example, in Rule 243, we might say that the pattern is 0, 1 stripes. And by the way, while Descartes wrote the colors as 1, 2, 3, my naming system starts with 0, so it has colors 0, which is the starting color, and colors 1 and 2. And while it is that, it would also be correct to write it as a 0 shell than a 1, 0 shell repeating forever. In Rule 342, we might say that the pattern is 201 stripes, but it would be more correct to write it as a 0 shell than a 1 shell, then the sequence of a 201 shell, then a 102 shell, then a 012 shell, repeating forever. Now let's look at Rule 407, which is a pattern called triangles. And while it might look complicated, it's actually pretty simple. It's a 0 shell followed by a 120 shell, then a 202 shell, then a 100 shell, repeating forever. In Rule 412, we have a pattern called polka dots, but it's actually just a 0 shell, then a single 120 shell, followed by the 122 shell, which repeats forever. Here is something slightly more complicated. In Rule 456, we have our first example of transient cells in repeating patterns. Here we have a 0 shell followed by a 1-2 shell, a 0-2 shell, and then a 0 transient cell followed by a 1-2 shell, then a 2-0 shell, and the pattern repeats. And now let's look at some of the more complex repeating patterns. In rule 288, we have a pattern called pillars, which has these pillars going infinitely downwards. And now I want to introduce a clever shortcut to show patterns more easily and simply. Instead of writing the shells themselves, only write their sizes and the number of transient cells before them. While we can still see patterns in the shells themselves, this will become really useful for progressively more complex patterns. Here the sizes say 1, 2, 2, 4, 8, 8, and then 3, 8 repeating forever, the 3 being the number of transient cells. This shows that the pattern is clearly repetitive. In fact, it isn't just repetitive, it's the same. If you look at the shells themselves, you can see from a certain point the shells just start being the same, namely 100 transient cells followed by 100 shell. And it is these shells being the exact same that produces those pillars. In rule 370, we have a slightly easier platforms pattern with shell sizes 3 and 1, 3 repeating forever, namely a 0 shell followed by a 1 shell, and then repeating forever a 2, 0, 1 shell, a 1, 2, 1 shell, a 1, 2, 0 shell, a 1, 1, 2 shell, a transient 2 cell followed by a 1, 2, 0 shell, and a 2, 1, 1 shell, and the pattern repeats. In rules 406 and 478, we have a unique pattern that has shell size of 1, and then repeating forever 3, 2, 3, 6, 3, 4, 3, 4, 3, 2, 3. Those namely being a 0 shell, then repeating forever a 1, 2, 0 shell, transient 1, 2 cells followed by a 0, 0, 1 shell, then transient 1, 2, 0, 2, 0, 1 cells followed by a 0, 1, 2 shell, then transient 1, 2, 1, 2 cells followed by a 0, 1, 0 shell, then transient 1, 0, 0, 1 cells followed by a 0, 1, 2 shell, then transient 1, 2 cells followed by a 0, 1, 0 shell, and the pattern repeats. And now onto the most complicated repeating pattern, which is the platforms one that exists in rule 261 and many others. It has shell periods of 1, 2, 4, 4, 8, and then repeating forever 8, 8, 8, 8, 8, 8, 8, 8, 8, 8, 2, 8, 8, 1, 8, 8, 8, 8. Those namely being a 0 shell, a 1, 0 shell, a 1, 2, 0, 0 shell, a 0, 1, 0, 0 shell, a 201001001 shell, and then repeating forever a 120120000 shell, a 012010112 shell, a 201200001 shell, a 1201012 shell, a 012000012 shell, a 201012001 shell, a 1200012 shell, a 0101212 shell, a 200012001 shell, a 1012012 shell, transient 12 cells followed by 0120120 shell, a 0120120 shell, a transient 2 cell followed by 0120120 shell, a 1201210 shell, a 0120120 shell, and a 20120101 shell, and the pattern repeats. Now on to recursive patterns, and here I will stop using the shells themselves for the most part because they would be of little use now and start using mostly the shell sizes. The most simple recursive pattern in this cellular automata is called the Sierpinski triangle and has a pretty simple form to it. For example, in rule 252, it has sizes 1, 2, 4, 8, 16, 32, and so on. So the sizes are the powers of 2, and the number of times they occur is the previous number of the sequence. For example, 8 occurs 4 times, and 16 occurs 8 times, and so on. That principle is what makes this a recursive pattern, as while the sizes do increase, they increase more slowly the higher the size. And also you can see patterns in shells themselves. For example, the first shell of a new size is always half ones and half zeros, which shows that the pattern is clearly non-chaotic. Now, there are a few patterns that are similar to Sierpinski's triangle. The Sierpinski's lookalike group, which has rules 320 and more, has shell periods of size 1, 2, 6, 12, 24, and so on. So from 6, these are the numbers that are 3 times of a power of 2. And it has the same property as Sierpinski's triangle of that the number of times they occur is the previous number of the sequence, which makes it clearly recursive. And if you look at shells themselves, there are some clear patterns there too. Now, there are also 2 outlying patterns that are also recursive. Rule 318, which is called nuclear reactors, has shell periods of size 1, 2, 6, 18, 54, 162, 486, and so on, which are the numbers that are twice of a power of 3, and it also has the property that the number of times they occur is the previous number of the sequence, which makes it clearly recursive. And also there is rule 410, which has shell periods of size 1, 3, 9, 27, 81, 243, so the powers of 3. Except this one works slightly different in that the number of times they occur is not the previous number of the sequence, but coincidentally, the rule sizes in rule 318, so 1, 2, 6, 18, 54, which are twice a power of 3, which means it is also clearly recursive. Now on to chaotic patterns. Here is where things start to get complicated, because what I found is that the boundary between chaotic and periodic patterns is not as simple as I previously thought. Here Decker classified 13 chaotic patterns. Of these, I would say that 2 are clearly periodic, 4 are clearly chaotic, and 7 I'm not sure about, they're 50-50, could be either one. First, clearly periodic. Here we have one type, which was rules 371 and 414. Now, these look clearly random, but there is a reason for that. That is because its shells in order have size 1, 1, 3, 3, 9, 9, 27, 27, 81, 81, 243, 243, 729, 729. Which means that this pattern exhibits exponential growth. And while it is clearly periodic, we cannot possibly describe that visually because of just how fast the shell sizes grow. Now on to clearly random ones. In rules 397 and 408, we have the same pattern, which has shell size length of 139, 18, 36, 72, 144, 288. But not only we transition between those at completely random times, the transient cells before stable patterns exhibit clearly random behavior, and just the way this pattern works makes me confident in that it is completely random. Rule 409 is similar, having the same shell sizes, but transition after different number of shells and having a different random pattern of transient cells. There is also rule 443, which also has the same shell size, but also transitions after different number of shells and has a different random pattern of transient cells. And it's more the fact that there are 3 completely different patterns which have the same characteristics here, which makes me believe that these patterns are random. Now to the patterns that are somewhere in the middle. For rules 415 and 469, it is sort of the same as exponential growth pattern of rules 371 and 414, except it has a seemingly random number of transient cells before them, and while I want to say it is random, there is just not enough data to decide conclusively because of exponential growth. Now on to rule 428, which looks really random, but might not be, considering there are no transient cells in the pattern, which are usually the sign of randomness. And its shell size has a pattern of being 27 times a power of 2 from 54, which is clearly non-random. But while I think it is not random, I can't conclusively prove it, considering the shell sizes transition after a seemingly random number of shells. So here I just can't really tell. Now onto the 2 patterns which I think are the closest to the border between order and chaos. And these have a similar pattern. In rule 343 and 411 and 463, from a point all the shells are size 6, except it seemingly has a random number of transient cells before them. But on second look, these actually have a pattern of starting from 7, the sequence repeats every 10 numbers. And while I feel like this makes it closer to an ordered pattern, whether it actually is anybody's guess. The second one, rule 447, I feel like is the most interesting of them all, as it has a clear boundary between order of size 2 shells and chaos of random transient cells. On second look, if you look at their differences, they seemingly do have some order, but I can't quite find a pattern here, so I feel like this rule is closer to chaos than the previous one, but whether it is again anybody's guess. I hope you enjoyed this new perspective on Cellular Automata and found this interesting, and I'll see you in the next one.